So hello there, classmates. This is mapping landslide activity and mapping landslide activity in SAR imagery or synthetic aperture radar. I'm Mitch Thompson, and my project partner was Leah Minnick, and with special credit to Elsa Kohler for some code and a lot of help and mentorship and guidance. Just FYI, Leah's internet connection and Wi-Fi is sketchy, so sometimes she'll pop in and out. If that's the case, I'll fill in. So why landslides with synthetic aperture radar imagery? Basically, landslides are very costly in terms of human lives, in terms of the destruction they cause, in terms of ecosystem and environmental destruction, not only just the property damage. And the verification of landslides are hard to come by on a broad scale, and synthetic aperture radar, with the beauty of it being all weather day night, you can image in broad scale from space regardless of the weather. And a lot of times landslides can be driven by climate change and increased urbanization. So, a lot of precipitation or runoff can cause landslides, in which case there will probably be cloud cover involved. So synthetic aperture radar can see right through the clouds and get to detection of the scar that the landslide leaves behind. So our project goals were to integrate an existing, we call it low accuracy, large spatial scale landslide database with the SAR imagery. And this database was built by previous cohorts in the program. So what we did is we took that database and we compared it to Sentinel-1 synthetic aperture radar data holdings inside of Google Earth Engine. And the second project goal is to create reproducible code to do just that, to integrate SAR and the Google Earth Engine and the power of that compute with the landslide detection and monitoring efforts of the global landslide detection catalog. So our approach, you'll see there in the workflow, our approach was to take that landslide, the verified landslides, and construct a geodata frame. And then from that data frame, we would build an AOI selection through a user input. So it's interactive Jupyter Notebook and reproducible code. So you'd enter the slide identification number, which you'd get off the full map that we built, as you see there in the GIF. So you'd enter the slide identification number into the Jupyter Notebook, and that would go query against Google Earth Engine in the Sentinel-1 holdings, in which case it would return an image list there you see to the right. And the image list is bounded by the bounding box that we create off of the landslide database, and then bounded by 180 days on either side of the confirmed event. And then we, just for verification and kind of a quick look, we would take the base maps of Google Earth Engine there on the left side of that sliding scale and an NDVI to try to confirm that indeed in the passive remote sensing technologies, we do indeed have something to look for in the SAR. And then from there, we would clip the image and then build a statistical change detection model in the SAR that would give us basically the bounds of the destruction and the landslide scar. And I'll turn it over to Leah for the rest of the presentation.
Thanks so much, Mitch. So as we ran through the notebook, we came across a couple of fails, but we also had some successes. So I'm going to talk about our results. So the first set of images on the left, highlighted in red, we have our output is, like Mitch was talking about, the definite change. So what you see highlighted in blue, those are the definite changes that occurred from that slide image that you input in the beginning of the notebook. So that location pulled a specific time, the event date, and that's what we were looking for in the final image. And so we could tell that this landslide, this particular location, showed significant activity.
Oh, looks like she dropped off, so I'll pop in real quick. So it showed significant. Oh, you coming back?
Sorry. Yes.
There you go.
Thanks for popping in. But I was just saying that that red shows us that we can see that landslide there. So that's a cool reference image to see. So that
Dropped her again. So another fail that we have is the speckle from the water. You'll see here in this area. There you go. You coming back?
Hey.
There you go.
So the second image series, the fails, is that there's motion in water from waves. So any AOI, any area of interest near water, is going to have a lot of motion. So in the future, we would apply a water mask to that. Additionally, with that, we have the croplands as well. So like the image in the center on the bottom, there was a lot of motion in that time date, because I think maybe those crops were harvested around that area or something similar to that. Maybe it was a mudslide and that kind of muddied that area. So that might influence our final assessment. And then on the right, we see that there is a lot of change in the first image. On the top, we see that there's a lot of that cyan, that definite change, but that's all of the images together. So when we pulled out the event date on the bottom, it shows minimal change. And so this is showing us that maybe we had the event date wrong, or it's possible that it was a mudslide that occurred across a long time scale. And so that change wasn't just one specific date and time. It occurred over a long time scale. So that would be something that our analysis would not pick up in the end. If you want to go to the next slide, Mitch. So then our successes, we can see on the left one, when you kind of look closely on the top half of that river bend, it almost looks like a landslide just from the satellite image. But then when we overlay it with our change detection, we do see that it shows that definite cyan color, so that definite change. So that was a success in my eyes. There was a match there. And then in the middle, this is the big SAR landslide, which is on our database. It was noted as a very large landslide. So that was something that I was hoping we could pick up. And so it did show those changes. Although we do see a lot of the motion from the waves, that's the noise in the bottom left half. We also do see where that land had shifted. So that was something that we noted from that landslide. And then on the right, this one was awesome in my eyes because it was a very small landslide, and our analysis picked it up. So you see underneath the house there on the top image that there's sort of a blank field look on a hill. But when you really zoom in, it looks like that land had given way. And so our analysis picked that up. And so we see some of that definite change in that cyan color. So that was a really cool one because it was a little bit smaller. And our satellite image, because it was a really recent image taken as a base map, it didn't correlate necessarily with the landslide event date itself. And so we hope in the future that we could integrate Sentinel-2 and have Landsat imagery that corresponds with the event date, so that in the future you could see really that exact change from that base map. So that's something that we can look forward to. And then to conclude, we believe that SAR is a potential really good tool to leverage for rapid landslide detection, especially across large scales, like large land areas, as well as remote locations. So one thing that I also noticed when looking through our database was that there was a lot of landslides reported near urban areas. And so one thing that SAR could be really useful is detect.
Oh, looks like we lost her again. So I'll just try to, finish her sentence is that in urban areas, SAR can, depend on the resolution. There you go. Coming back.
Hey.
Yep.
So I believe that the remote locations showed up the best, and that could be really useful because they're the least reported on, and literature points as a need to have a little bit better detection of these locations. So this is really cool because we saw a lot of the landslides that were more remote were a little bit easier to show the change. And I think that's because they were not showing the urban areas, and that could include development, that could include other background noise parameters that might influence that change detection. So this could be a really great tool in the future to monitor and detect landslides in the future. Mitch, do you have anything else to say?
I was just going to add that depending on the resolution, because Sentinel-1 is a pretty coarse resolution imager. So in the future, we could integrate some commercial SAR that can image, in about 30 centimeters to 50 centimeters resolution. And that means that objects on the ground need to be 30 to 50 centimeters apart from one another in order to be resolved. So it could be used for urban areas as well. However, the algorithm that we were using was a statistical change over multiple images. So if you think about that, 180 days on the other side of the event, the urban areas, there's a lot of change happening inside of urban areas. So kind of what, just backing up what Lee was saying about the rural areas. And finally, one of our biggest challenges was working with the Google Earth Engine API. So we had to learn that API and how to make function calls to it and how to get results out of it. So that was a very, very big challenge for us.
And Google Earth Engine is typically JavaScript. So when you run it on the script itself for Google Earth Engine, it is in Java language, which we weren't trained in, or at least I wasn't. So that was tricky when you were Googling solutions to certain issues. A lot of what I was getting was the Java language. And so that for me was a tricky interface because it really made you think a little bit harder on how to solve some problems. But I'm excited about our results. I think it's a great start. I think we already have a list of ways to improve our notebook if we had more time and resources. So hopefully this could really serve future investigations on landslide detection. So thank you guys.
Yep, thank you.